Good day, everyone. How are you? I will continue to discuss with you the problems we started yesterday. Problems 90, 91, 92, 93, and 94. Okay? So this time, I will be just giving you some general guide. Okay? Unlike the problems I discussed with you yesterday, March, July 13, okay, Monday. Today is July 14, 2020, Tuesday. Okay, I have with me here the book, and I said yesterday that problem 92 is similar to problem in example number 10 of chapter 5. You know, every chapter there are examples, and the authors believe that these examples will help students understand the concepts and the principles. And so, example 10 is applied to problem number 92. I will read the problem. Okay? An elevator consists of an elevator cage and a counterweight attached to the ends of a cable which runs over the pulley as shown in the figure. The mass of the cage with its passengers or load is 1,200 kilograms, and the mass of the counterweight as shown in the diagram on the drawing provided by the book is 1,000 kilograms. Suppose that the elevator is moving upward at a speed of 1.5 meters per second. When its motor fails, while moving upward with a speed of 1.5 meters per second, there is this mechanical problem. The motor of the elevator system fails. The elevator then continues to coast upward, meaning move upward, until it stops. Of course, we expect that to stop because there is no more operation of the motor. It fails. So it continues to move upward, but this time the speed of the elevator would be decreasing speed. Why? There is no more mechanical power coming from the motor. So it will slow down in going up until it stops. Okay? And then momentarily stops only because after that it will begin to descend. It becomes a free fall. Okay? And begins to fall down. After that momentary stop, it begins to fall down. Assume no friction. Of course, in the reality, there is always friction. But the purpose of this problem in assuming that there is no friction is to simplify, because if there is friction, then we need to involve the force of friction in the equation. Okay? Without the involvement of friction, because friction is assumed to be absent, which I said a while ago, in reality there is always friction, but the authors would like to make the problem simple as possible. So this is now the simpler form of the problem without friction. Okay? And assume the emergency brake of the elevator, because the elevator, any elevator has emergency brake just in case there is a failure, either mechanical or electrical. Okay. Brownout, electrical. Failure in the motor, mechanical. The emergency brake of the elevator does not engage until the elevator begins to fall down. So there is this assumption that there is no engagement of the emergency brake. The system is allowed to go down. The cage is allowed to go down. The brake locks the elevator cage to its guide rails. In other words, it follows that rail. There is that guide rail, okay? It is being followed there because there is that brake locks. What is the deceleration of the elevator? How long, meaning to say, we see what is the deceleration of the elevator. So we are expecting here a negative acceleration, because deceleration in mathematical terms, it's a negative acceleration. How long does it take to stop? It will stop, of course. How long? How many seconds? Letter B, what is the tension in the cable when the elevator is coasting up? So there is the tension. Tension is a force in the cable provided by the cable, exerted by the cable. Okay, what is the tension in the cable when the emergency brake has engaged and the elevator is stopped? Okay. So you have here the drawing. There is that drawing. Okay. I'll try to draw this one, Draw this one as good as possible. Okay. You have here the cage. You have here the cage. Okay. This is the cage. The load is here, the passenger or whoever or whatever inside the elevator here. Okay. Then you have here the cable wire. The cable wire. This is the counterweight. Okay. Of course, you have here the pulley. There is this pulley here. Okay. Then the elevator cable, okay, moving around the pulley. Okay. Okay, this is the elevator. Given the weight of the elevator, This is the weight of the elevator. This is the weight of the counterweight, W2. Okay? There is tension here. Tension is always away from the body. This is the body. Tension is always directed away from the body. Tension. Okay. There is also tension here. Tension. Okay. Now, going up. So, the system here of objects, the cage and the counterweight, including the pulley, and we assume the pulley to be frictionless, the cable without friction, they are all governed by the second law of motion, that F equals ma. So, second law of motion, you have here F equals ma. When you solve this particular problem, you are going to isolate one body, the cage, from the other body in your analysis with respect to forces acting on the body. So, first let us consider this first body. Okay. First body, M1. Second body, M2. Okay. Now, let us consider the force acting here. The force acting on this body, the net force acting on this body, disregard this body because we consider this one as a single body without involving this one. Okay? Okay, now, so, in the case of this body, there is that force F1. F1 equals M1A1. So therefore, the force F1 there is that net force acting on the cage as the mass 1, the object 1. Okay? So, you have here the mass of the cage having M1 and the acceleration of the cage A1. Okay. And this is equal to M1 A1 is equal to T. Okay, it's moving up, so T minus M minus W1. Okay? And then the tension here. Why not reverse W1 minus tension 1? That we cannot do. Why? Because the tension is able to pull up the cage. Okay? So there is greater force by the tension against the weight. W1. Why do we say that there is greater force in tension against W1? Well, the problem is telling us that this cage is moving upward. So the tension is stronger than the weight 1. Weight is also a force, but compared to the strength, tension is stronger. Again, the cage is able to go up. If it is not able to go up, instead going down, this one is stronger. So, W1 minus tension. But here, the problem is telling us it's going up. going up. So therefore, tension is pulling the cage with a greater force. So that's why T minus W1. If the cage does not have weight, T minus 0, no weight. But there is weight there, as given. Okay? W1, the weight here, the weight here is equal to M1G. Okay? That's the weight. Okay. And we can have this equation as M1 A1 equals T minus the M1, okay, M1 G. Okay? So, we call this one equation number 1. Equation number 1. And equation number 1 is derived out of the given quantities on mass 1 or cage. Okay. Then, let us have this one. The force according to the second law of motion F equals ma for block with mass M2, okay, or for this counterweight with mass M2, according to the second law of motion, F2 is equal to M2A2. Meaning to say, the mass of the counterweight, M2, times the acceleration of the counterweight, A2, is equal to, okay, remember this is going down, this one is going up, the elevator is going up, counterweight is going down, is equal to W2 minus tension. Here, T minus W1. But here is W2 minus tension. Why? It is going down, therefore the weight 2 is stronger than the tension. Because this counterweight is able to go down against the tension, therefore the force of this weight is greater than the tension. That's why W2 minus the tension. And so, you have here M2 A2 equals W2 minus tension. This is equation number 2. That's equation number 2. Okay. So we have 2 equations now. Let us go further in our analysis. This object is moving upward with an acceleration. This object is moving downward with an acceleration. The acceleration of this object here is A1. The acceleration of this object here is A2. So it is moving with acceleration A1. It is moving down with acceleration A2. And so when we say acceleration, it's either increasing speed or decreasing speed. In this case, as it goes up, there is the motor failure. There will be a slowing down. Slowing down, slowing down, slowing down, slowing down, until it stops. Then, going down, going down, going down. That's it. That is the situation. Okay. Now, When this one moves slowly up, what happens to this one? This one will also move slowly down. If this will stop, what do you think will happen to this one? This will also stop. If this one moves faster, this one will move faster down. Slower up, slower down. Why is it so? Why? Why? Because the two objects with M1 and M2 as their masses are connected with one cable. They are connected with one cable. If this moves faster, this one will move faster. If this one will move slower, this one will move slower. Slower down, slower up. Faster down, faster up. Stops, stops. Okay? Therefore, what is your conclusion with their acceleration in terms of magnitude? In terms of magnitude, how fast or how slow. But in terms of direction, opposites. One is going up, the other is going down. But in terms of magnitude, how fast or how slow, what do you think their magnitude of the acceleration A1 versus A2? Ladies and gentlemen, that question I will answer. The acceleration here in terms of magnitude, because this is a vector quantity, this one is a vector quantity, this is a vector quantity, this is a vector quantity, meaning to say magnitude and direction. Acceleration is a vector quantity. So we get the magnitude only, scalar magnitude, because a magnitude is a magnitude. A direction is a direction. Combine them, magnitude and direction, you have a vector quantity. Okay? So, the acceleration, okay? The magnitude of the acceleration, magnitude, absolute value, is equal to the magnitude of the acceleration of body 2. Body 1, acceleration A1, body 2, acceleration A2, their magnitude are equal to each other. Okay? They are equal. Why? If this one will move faster up, moving faster down. If this one will move slower, this one will move slower down. If this will stop, this will stop. So, that happens because they are connected with the same cable. Okay, now, so therefore, we can say here that A1, if we have the magnitude, we get the absolute value, therefore A1 equals A2. So A1 equals A2, and therefore we can just designate that as simply A, because they are equal. So let us just call that as A. Body 1 has acceleration A1 equals A. Body 2 has acceleration A2 equals A. Okay. So therefore, from equation 1, you will have here M1A, no more subscript 1, is equal to T minus M1G. This is equation 1. Equation 1. The difference, no more subscript 1. Okay. For equation 2, you have equation 2, M2A, no more subscript, equals W2 minus tension. W2 minus tension. W2, that is equation number 2. So, this is our equation 1A. Now, this will become equation 1A. And this one will become equation 2A. Right? Or, so that you will not misconstrue the A as acceleration, 1A, 2B. Big letters A and B. Next, we are going to get the summation. We sum up. We are going to sum up because there are forces, and usually if we would like to get the resultant force, we are going to sum up all the forces, summation of forces. In other words, there are forces here, so we get the summation. Summation of forces is equal to F1 plus F2. We are going to sum up. Okay? We are going to sum up this one. F1, this one is F1, this one is F2. Sum up there, therefore we add. Okay? We are going to add them. So when we add, you will have here M1A plus M2A. So we add M1A plus M2A. Add equals, you add this one, tension minus M1G. Okay? This is the weight. And by the way, I'm going to erase this, W2. W2 is M2 over G. So I will write here W2 because this one is W2, M2 G. So we add T minus M1G, T tension minus M1G plus M2G, okay, minus T. So, there. So, we added. Okay? So, when we add, what will happen then? You have, we simplify. A is a common factor. A is a common factor. So, we factor out A. So, M1 plus M2 equals, we cancel out T and T. T minus T. No more T, zero. So, what remains is this one. What remains is this. You have here M, I rearrange. G minus M1G. The tension here, T minus T, T minus T, cancel out. I rearrange. Positive M2G minus M1G. Okay? And we continue M1 plus M2. We factor out G because G is a common factor. So you have M2 minus M1. Factor out G because G is a common factor. And the problem is asking for the acceleration. Acceleration, therefore, is equal to, by cross multiplication, M2 minus M1 G over cross multiply M1 plus M2. What remains here is A because this one, this factor is being cross multiplied here. this becomes the denominator by cross multiplication. So, you will have here, okay, this equal to, simplify further, minus M1 over M1 plus M2 times G. So there you are, then you substitute. We substitute the value. And you have the value there, we substitute. Okay? We substitute. Our M2 is given. What is our M2? This is the mass of the counterweight. In the problem, I'm looking at the problem, the M1 here, problem M1 is 1,200 kilograms, M2 is 1,000. Oh. So, you substitute here, you do the solutions here. This one is 1,000, this one is 1,200, 1,000. The mass here, this one is 1,200. So 1,000 minus 1,200, you will expect a negative acceleration. You will have a negative acceleration. Why negative? Because the speed is decreasing until it stops. The result here is negative, huh? Because M2 is 1,000 minus 1,200. 1,000 minus 1,200. The answer is a negative. You divide this one, the negative divided by this remains negative times G 9.81. Final answer is a negative acceleration. And then that negative acceleration, you are going to use that in finding what will be the, how long will it take? The next question is how long? How long? The next question, the next question is how long does it take to stop? So slowing down until it stops here. Of course, this one will also stop. In the process of stopping and finally stops, how many seconds it will take to happen? And so, what equation to be used? Remember our formula: acceleration equals final speed minus initial speed over the time. Time, therefore, time is equal to final speed minus initial speed over the acceleration. Substitute. Final speed is 0. Initial speed. What's the initial speed given? According to the book, it is moving with a speed of 1.5 meters per second. Substitute. This is negative. From the result here, negative, ha? The result in the numerator is negative because 0 minus 1.5. 0 minus 1.5. 0 minus 1.5 equals negative 1.5. Negative 1.5 divided by negative acceleration, the answer is a positive seconds. It will be in seconds. Final answer will be in seconds. I am interested to see your solutions, showing the units, and you cancel out the units. You always do that, huh? When you solve, show complete solution. Show the units. Cancel them. Show how you cancel them. Until finally, you have the final answer with the correct unit. Okay. Okay. This equation. Then, you are asked of the tension. What is the tension of the elevator? So, tension, you can get the tension here or here. Better here to get the tension. Okay? This equation 1A. Equation 1A. I'm going to erase this one, ha? I'm going to erase this, ha? I'm going to erase this. Erase. I am going to erase. I'm going to erase this one. Erase this. Erase. Also this one, I'm going to erase. Erase. Erase the writings by the eraser. The eraser erases. Okay. So, you are asked of the second question. What is the tension? Use this equation. Equation 1A. Equation 1A is telling us M1A is equal to tension minus M1G. This is equation 1A. This one is equation 1A. Equation 1A. So, tension is equal to M1A plus M1G. M1 refers to the mass of the kids. A, acceleration coming here. G, of course, 9.81 meters per second squared. You indicate all the units. Okay? Okay. So, you already solved the problem. And then, the next question is, what is the tension in the cable when the brake, emergency brake, is engaged and the elevator stops? What do you think? When the brake is applied, emergency brake applied, of course, the elevator, the counterweight will stop. And when it will stop, what is the tension in the cable? Because the tension has a force of carrying the cable. This one, even if this one will stop, the tension remains there. But how much is the tension? What is the amount? What is the amount? The tension here is different from the tension here. Different, ha? Why? The tension here, there is motion. That's why there is acceleration. There is acceleration. There is motion here. But in problem or question number 3, what is the tension when the cage stops? When this one will stop, this cage will stop, the counterweight will stop. At rest, what is the tension? So there is no more acceleration. So what do you think? Find it out, ha? You can just find that answer here. Okay? What do you think? If the elevator stops, what happens to the acceleration? And if that is the acceleration when the elevator stops, what is the tension? Tension? You are going to ask that. Okay. You are going to solve that. Next. This one. Problem 93. Okay, problem 93. I'm going to erase this one, ha? I'm going to erase, ha? I'm going to erase, okay. Erase by the eraser. The eraser is controlled by the teacher. So the teacher is controlling the eraser to erase the writings on the board. Okay. erase, erase, erase. Okay, okay. It's now being erased. So, where are my... Okay, this one. You have this problem, number 92. I will just draw this one immediately. There is this table. You have here a pulley. There's the pulley here. Then this is the pulley. Then you have here the string. Then there is the block here. Which is bigger here? Smaller. Okay, smaller. Okay. So this one is M1. This one is M2. And the surface where the block, where this block M1 lying is without friction. In the Cebuano, a surface without friction is danlog, slippery. Without friction, slippery. The surface must be very smooth. So even if M2 is smaller, the block will be moved by this M2. The M2 is connected to a string, a rope, whatever. Is this a string? A roundtable hanging light string. It is a string pulling block 1. So block 1 bigger, larger. Okay? Block 2 is smaller. But still, block 1 will move because the surface here is without friction. Therefore, the surface is danlog. Danlog is slippery. See now, smooth. There is no friction. If the surface is rough, probably this one will not be able to move block 1 because block 2 is smaller. Assuming they are made of the same materials, this is a wooden block, this is a wooden block, and the same kind of wood, maybe lawaen or kemagong, or ipel, the same kind of wood. So we expect that this one, okay, this one, if this is rough, this one will not move. But because this is smooth, even if this larger, this one will move. This one will move in that direction because there is that force. We call this one tension. It will move. Dako man ni sir. Dako pero danlog. This will move. But if this surface is rough, rough means the opposite of danlog is sapnot. Okay? Subknot. So, lisod. Very difficult to move because it's rough. Okay. Now, the direction there. The direction here, down. Okay. Now, there is no fraction here. So, therefore, there's no need for us to get the normal force. There is a normal force here, by the way. There is a normal force. There is a normal force here. And of course, there is that force due to the weight. There is the force of weight, W1. But N1, the normal force, canceling weight 1. If there is friction, then that is another story. Because we cannot neglect the normal force anymore. Why? Because in friction F, you have this formula, friction, the force of friction equals the coefficient friction times the normal force. And the normal force is the force exerted by the surface against the block. Okay? The block exerts a force against the surface, and that force exerted by the block is what we call the weight. Okay? The weight is pressing down the block. The pull of gravity is pulling the block down. The surface where the block is lying reacts, and that reaction force is the normal force. And because there is no friction, okay, friction is zero, so no need to have the normal force. So what happens here is, there is this weight 1 cancelled out by the normal force, so the net force here is the tension. Okay? The net force is the tension, and you have here the force due to the weight, W2, where W2 equals M2G. Okay. Then you are asked of the acceleration. The problem is asking for find the acceleration and find the tension. So, we started in problem 92 with the second law of motion. F equals ma. We do the same in this problem. In the case of block 1, M1 is equal to M1A1. That is what we did. Is equal to the tension. Okay? There is the tension. Okay. Then F2 is equal to M2A2 is equal to W2 minus the tension. W2 minus the tension, not tension minus W2. If we have tension minus W2, then this is going up. But because it is going down, it is the weight minus the tension. Weight 2 minus the tension. Okay? Okay. Then, the same, we have the assumption that A1 equals A2. And therefore, we say it is equal to A. And so, for this equation, M1, A1 becomes that equals tension. For this equation, you will have M2A is equal to W2 minus the tension. Okay? And further, we simplify this one further. Okay? W2 here W2 is M to G. So W2 is M to G. W2 M to G. W2 equals M to G. M to G. That is our W2. Then we are going to add, okay, we are going to add, we always get the summation of forces, we add. So you have here M1A, okay, plus M2A is equal to T plus M2G minus T. We factor out A because A is a common factor. A, factor out. And then T minus T is 0, so you have M2G. No more T because T tension cancelled out. Okay. And so, first question, what is the acceleration? Acceleration therefore is equal to M2G over M1 plus M2. Or we have to simplify this one as M2 over M1 plus M2 G. What is the tension? Find the tension. It is already your work. Tension. What is the tension? Find it. To find the tension, use one of the equations here on the board. Okay? Then, we proceed to the last problem, 94. Okay, last problem, 94. In the last problem, 94, what will I do? I will erase. I will erase this. I will not erase. Okay. I will not erase. So the problem is like this. The problem is this one. There is the pulley. Then Black 1, Black 2, Black 3. I will just give you the initial. You are going to finish the rest. Okay. There is tension here. This is what we call tension 1. There are two strings here. String 1, string 2. There are two strings, String 1, string 2. String 1, string 2. One string, second string. String number 1, string number 2. Two strings. This block is pulled by the string number 1. Okay? This block 2 is also being acted on by string number 1. And so this is also tension number 1. Remember, tension is always directed away from the body. Okay? Then, string number 2. There is the tension coming from string number 2. Tension 2. There is this tension. This is now a challenge. Out of the 3 problems I presented to you now, there are 4 problems. 90, I solved that for you, but you have to resolve that, recompute that. Problem number 91, second problem, I presented to you how it should be solved. 91, 92,